All right. So greetings, everyone who is attending this webinar. I'm Vinayak Krishnamurthy. I'm an assistant professor in the Department of Mechanical Engineering and also affiliated with the Computer Science and Engineering Department at Texas A&M. And as they say in Texas, howdy, howdy all. I hope you'll enjoy this talk. I'm quite honored and very excited to present this work on motoric and perceptual kinesthetic symmetry in two-handed or bimanual interactions. So this work was done by my PhD student Ronak and Riddhi, who's my master's student, and Ronak recently graduated. He's working with Facebook Reality Labs, and Riddhi is also going to graduate in December. So it's quite an exciting time for everybody. Now, in all honesty, I want to start this presentation by giving you the real origins of this work. So this work originated as an amusing thought experiment in one of our lab meetings, right? We had nothing better to do after we had discussed everything. So I posed the following question to my students, right? So I said, well, suppose you have a magical rubber band or a spring, right? You're holding the spring and you're pulling the spring or the rubber band with both hands symmetrically away from each other. Suppose this rubber band stops giving you the reaction force feedback or the spring force feedback on one of the hands and doesn't tell you. What stiffness should the spring be so that you can't tell whether that happened? Okay, so it was kind of an awkward question. We started thinking about it, and after a while, we actually found out that this is indeed an important question to answer from the point of view of motoric and perceptual symmetry. So there is, it appears that there is actually a nice background to this idea of kinesthetic perceptual symmetry that I'm going to start with in this presentation. So if we think about it, perceptual symmetry is where the tendency to be symmetric in a two-handed movement is not dependent on the muscular or motor constraints. That is, it is not dependent on some prior connection between my muscles on the right hand or my muscles on the left hand, but rather it is perceptual in nature, meaning that it actually comes from the brain. It comes from how our mind perceives, right? And this was a very seminal work. This was a seminal discovery that was published in 2001 in a Nature paper by Mexner and group. And this sort of forms the basis of this work, right? So essentially, even though we have, symmetry across muscle groups, right? What we usually in literature prior to this work, people believed that the reason why we are able to do symmetric operations is because there is some innate symmetry in our neuromuscular structure. This paper actually showed that what really happens is the signal for approaching that symmetry comes from the brain directly, okay? And it can manifest in visual symmetry or in auditory symmetry or in kinesthetic symmetry as well, right? So this paper was particularly about kinesthetic symmetry, okay? So the broader question that we wanted to address in this work was, does this perceptual symmetry exist for an external force, that is kinesthetic feedback as well, right? And what's the intensity at which this force exists, right? So the inspiration for this work also came from something called the mirror box therapy. So imagine the following scenario. Suppose one of your limb is amputated, right? You don't have one limb, right? And you are feeling pain on the limb that is amputated, okay? So the sensation, there are, the people actually face this problem where they have a very sharp sensation of shooting, stabbing, or cramping, or burning, sometimes even scratching. Something as simple as not being able to scratch your arm that doesn't exist can cause extreme problems, both physiologically and psychologically, right? So this is also known as the phantom limb syndrome. So there's a whole bunch of people who looked at this idea of mirror box therapy, and instead of talking about it, I'll show you a small clip, right?
One answer might be that the brain is sending signals to the arm and trying to clench it, but in you and me, there's messages going back from the muscles of the hand telling you you're clenching too much or too fast, and this damps the command signals so you can slow down. But the patient has no feedback because he doesn't have an arm. So the brain says, send even more signals, okay? And this goes on, you get into a sort of positive feedback loop. So I said, well, if you give him some other source of feedback, such as visual feedback, maybe that'll trick the brain into thinking that the hand is clenching or unclenching, and maybe you can interrupt this loop. So I said, well, why don't we put a mirror there and have James look inside the mirror? It's as though you have visually resurrected the phantom limb. And of course, the patient knows it's an illusion, but it's very, very compelling.
Right. So this idea of using visual perception to trick the brain for spatial symmetry, this has been explored. Of course, there are pros and cons to the methodology, right? But the work still indicates, it provides a strong indication that spatial symmetry is rather a perceptual phenomenon rather than a muscular phenomenon. Okay. Now, so based on this, we looked at quite a few prior literature. So if you look at the general area of kinesthetic perception, people have done a lot of different varieties of works. For example, if you look at Baumeister and Whaley, they have looked at kinesthetic perception from the perspective of somebody being able to align oneself with the vertical using different kinds of cues like visual cues or vestibular cues, things that pertain to gravitational sensing and so on, or proprioception, right? And then in the recent past, people have also tried to integrate human-computer interactions or interactive technologies for exploring kinesthetic perception, right? On the other hand, we also have a lot of interesting work on specifically bimanual symmetric actions, right? So I already mentioned Mexner's work that essentially talks about how symmetry manifests in the brain rather than only in the muscles. But then later on, there's also this work by Wasaka that introduced a mirror as a visual means, as a means to provide visual cues for mirror symmetries in bimanual interactions. And then lastly, I want to highlight this work by Malabet in 2010 that also describes different types of symmetry. So if you look at these three diagrams, basically you can think about visual space symmetry being where your hands are essentially creating the same curve in space, right? So they are moving parallelly, okay? Then you have point mirror symmetry. So imagine that you have a point in space and you're sort of moving your hand around that point in a symmetric manner. Our current work, pulling of the spring, that pertains to joint space symmetry where we are in a mirror symmetric position, right? So the hands are moving in mirror symmetric fashion, okay? Now, we also looked at some work on disability and rehabilitation, specifically stroke rehabilitation. So there's a lot of work in robotics that talks about different ways to do stroke rehabilitation. Some uses kinesthetic feedback, some doesn't, right? Or uses it in different ways. And then there's also a lot of AR and augmented and virtual reality technologies that have been explored for quite some time now for rehabilitation, right? So amidst all this work, we were specifically interested in a more basic question, right? Is there perceptual symmetry in kinesthetic feedback? More importantly, to what extent can we identify it, right? So that pertains to how stiff should your spring be in order for you to be able to fool the person in thinking that both sides are getting forces, right? So that's kind of the question that we wanted to answer, okay? So in order to do that, we came up with a very simple experimental setup. Okay, let me move my camera here. Okay, so we came up with a simple experimental setup that has two haptics devices, right? So we use the Geomagic Touch haptics device, and they both have a stylus each, right? And we simulated a virtual spring. So what the user would do is they would hold the stylus and they would press both the buttons, and as they start pulling, both the styli, both the devices will give them opposing force feedback, right? And it was a very simple physical model. So we assume a linear spring, and therefore we are giving linear feedback with respect to the displacement or deflection of the spring. Okay, so with this setup in mind, we also had some additional visual cues. So this experiment did not have any screens, right? Because we did not want to sort of add visual cues and then not be able to tell what was happening because or without the visual cues, right? So we provided a simpler visual feedback where we said, okay, there are three linear references or references for straight lines. The user could comfortably place at one of these, and the task was to basically start at the center and pull as long as they want to, okay, as or towards the end of the line. So the lines provided a means to control or get some visual cue to control the motion of the hand, okay. So with this setup, our goal was to explore this perceptual aspect of kinesthetic feedback in this kind of a bimanual symmetric action, okay. So in order to achieve this goal, we experimented with, we recruited 14 healthy participants, and these were basically graduate and undergraduate students in the university, 18 to 30 years of age, right? And of course, we only had one left-handed participant, so 13 of them were right-handed, okay? And we conducted a within subject study where we have 4 conditions, right? So condition 1 is both the devices are on, which is your ground truth, meaning that is the way the spring is supposed to behave, okay? Then we have the second condition, which is we turn off both the devices, so there is no force feedback at all. And then the next 2 conditions are the device is on the dominant hand, and the next one is device is on the non-dominant hand. So the other 2 devices are other devices off, okay? And that's the asymmetric part of the experimental control, okay? So with this, we asked the user to do a very simple task. So before I move on to the task, I just want to mention that in order to properly parameterize the task for different stiffness values of the spring, we first did a pilot study for 5 of those 14 participants, where we varied the spring stiffness for all the 4 control groups that I showed you. And we found that there is actually a sweet spot range for people to be able to get confused, right? So if it is too low or too high, overarchingly, you don't get the effect of the study. Okay, so we decided to use the range of the stiffness between 5 newtons per meter to 9 newtons per meter. Okay. So with this in mind, the task was really simple. Okay, the user was asked to keep pulling the spring to the end of that visual reference line until they started experiencing unequal forces. Okay, so if they don't feel something is right, we ask them to stop there, and we would record how much they move. So at what length did they think that this is something fishy is going on? Okay? And the study was roughly 30 minutes because this task was very it's a very short-lived trial, right? So it's roughly 3 to 4 seconds per trial, okay, per pull of the spring, right? So the task was roughly 30 minutes, and we randomized across the different conditions, the 4 conditions, and for each condition, the participant did 3 trials. So essentially, every participant did 60 trials in a span of 30 minutes. Okay, and then we had both pre and post questionnaires as well. Okay. Now, in order to measure, this motoric and the perceptual symmetry aspects, there are several options that are available. So for each stiffness value and each condition, you can think about different motoric responses, right? So the simplest is position with respect to time, or velocity with respect to speed with respect to time for both the hands, right? That's one way of looking at how a person moved. On the perceptual side, we used the length at which the participant stopped, right? Another equally valid metric could be time. The reason why we did not go for time in this particular study is because people moved at different speeds, right? So we wanted to see how far they were willing to go in order to detect whether there was any asymmetry or not. Okay. A brief note on motor symmetry computation. So now suppose we have say the velocity or speed profiles of both the hands. So one simple way to think about it is in terms of detecting whether there is symmetry in movement is to look at the signals, the speed profile signals, and try to see how similar they are, right? So we use something called the Pearson's cross correlation and lag in order to understand the symmetry of movement. So the idea is simple. You have 2 signals. You take one signal and you move it along the X and at every movement, you are computing the correlation between the two signals. So wherever you get the maximum cross correlation, you essentially take that as your correlation value, and whatever you move, however much you move, you take that as the lag. So we used this cross correlation in order to understand the motor symmetry, and essentially high correlation with low lag indicates a reasonably good motor symmetry, right? And it's normalized, so it's between 0 and 1. Okay, right. So with that in view, let's look at some highlights of the results in terms of how people moved and what people felt. Okay, so let's look at motor strategy first, right? If for each of the 4 conditions, I'm showing you one plot where each box plot is one stiffness value. Okay, so I'm comparing across stiffnesses what happens in terms of the movement of the people, and the null hypothesis is that there is no significant difference in correlation coefficient if you vary the stiffness of the spring for any given control group. So if you look at each of these plots, so we did a univariate ANOVA for this. So the null hypothesis holds for all cases, which means that regardless of whatever control group we saw, participants were able to maintain symmetry of motion, right? And it was independent of the variations in the stiffness of the spring. Okay, so it means that as far as any external party could observe, they were all moving symmetrically, right? So muscularly, everything is symmetric. Okay, let's also look at the other way, the same data in a different light, right? So suppose now I say, well, let's look at each of the stiffness as a constant, and let's see what happened across the different tasks. Okay, so in this case, what we did was we did a pairwise comparison of the 3 cases. 3 cases are both are off, which is T2, dominant on T3, and non-dominant on, which is T4, with respect to the ground truth, which is when both the devices are on. Okay, so therefore you see only 3 p values for each of the box plots, right? In this case, my hypothesis is that there's no significant difference between a given group with respect to that both on group. Okay, when you change the control groups, okay, for a given stiffness. Again, you will see that the null hypothesis generally holds. P value is generally quite high. Okay, which means that, or which indicates rather that for any given stiffness, participants maintain that motor symmetry regardless of the conditions of the control group. So this was also, something that we wanted to happen, right? The motion should be symmetric. It's the perception that we wanted to see whether it changes, how it changes, and so on. So okay. Now let's look at the perception part of it. Okay, so what happens when we look at perceptions with varying control groups? Okay, and the null hypothesis is again that there's no significant difference across different control groups for a given stiffness K, right? So let's start with K equals to 5 newtons per meter. So here you will see that there is one case, which is the case that is when both the haptics devices are off, where we found significant difference. Not only that, here people took significantly longer, or rather they pulled longer, roughly by 4 to 5 centimeters, to be able to detect asymmetry. So this indicates, this is an interesting phenomenon. It indicates that when both the devices were off, they were trying to, they were confused almost all the way to the very end of their spring pull. They could not tell whether the forces were on, or one of them was on or off, and so on and so forth. Okay. If you look at a couple of higher stiffnesses, right, then you see that the spring lengths at which the participants stop are shorter by roughly 5 to 6 centimeters, specifically for the 2 cases where there is asymmetry. That is for the case where we switched off either the dominant device or the non-dominant device. So in both cases, you'll see that you get significantly different results with respect to the other 2 control groups, which is kind of expected, that people were able to tell in a short span of time that there was asymmetry as you increase the stiffness of the spring, right? When you go further higher in stiffness, that is again where you see something interesting happening. You will again see that there is a significant difference between both off case and the both on case, right? And people again did a very large pull, which was needed to identify asymmetry, right? So even here, perceptually, they were unable to see whether the devices are on or off. Remember, the condition is still symmetric, right? Both the devices are off. Okay, so it's a different kind of fooling the user situation, right? Now, if you look at the same data but compare it with respect to varying stiffnesses, right? So suppose our null hypothesis is that there's no significant difference across different stiffnesses for a given control group, right? So in this case, you will see that for the first two conditions, that is the top row, right? Top row, columns 1 and 2, you will see that when you think about both on and both off, right? Participants roughly move the entire length of the visual cue that we gave, roughly 23 centimeters on average, okay, to identify any asymmetry. But when single device is active, that is dominant off and dominant on, right, it is relatively easier to perceive the asymmetry at lower forces across all stiffness values. Okay. So with this, with these results in view, I want to share some insights, at least that were interesting to us, right? So these are the key takeaways that that we found interesting. First is we were very interested in knowing, whether there is a limit to the force that allows one to detect this asymmetries, and we found that people could identify asymmetry for a spring force as low as 1 Newton all the way up to 1.6. So that's the maximum. When the dominant device was on or off, right? So when one of the devices was switched off, okay? We also see that this symmetry is preserved from 0.8 to 1.5 Newtons in the condition when both the devices are on. So even when you're looking at the ground truth, even there is a chance that some people will have false negatives, okay? That they will say something is asymmetric when actually it is symmetric. Okay, so that was pretty interesting to us. We did not expect that. Okay, and one of the reasons was that we found that the dominant hand is very crucial for perceiving this asymmetry, right? Specifically, it creates false positives when you increase the stiffness for the case where both devices are on. And that's what you are going to see in the chart that I'm showing you on the right hand side. You look at the red box plot, you'll see there's a very large dispersion under the 50th percentile range, okay, for the first chart, right, on the left hand side. Whereas if you look at the case where both devices were off, right, at that time you will see people are still confused all the way up till the end, right? So they pull as long as they possibly can to figure out whether there is asymmetry or not. Okay, so we got some interesting ideas from this work. Let me remind you that I mentioned that this was essentially an outcome of a brainstorming in a lab meeting, right? So of course, there's a lot of things that we want to do and we plan to do. So there's a lot of possibilities of expansion. The first thing is, if we were to put this in a real context, I think it would be a very nice idea to produce similar data sets and analyze them for disabled individuals or people with strokes and things like that, right? So we collected data only for healthy patients. So we want to see whether the same patterns follow for people who have some motor response disability, right? Second, and this I think is all pervasive in many psychophysical analyses, and particularly for haptics. So we only have the users say right now that the length at which they stop. I'm really interested in seeing if we can augment this with other types of data, say for example EEG, to better figure out when the user starts to feel that asymmetry, right? And last is about the task, right? So in addition to the spring task, there are many other tasks, say for example visual symmetry, right? So suppose instead of pulling a spring, I have a stick, right, which has a weight, and I'm moving the weightlifting in the virtual world, right? here I have some interesting possibilities of shifting the center of mass in a more continuum fashion. So I can sample from a continuous distribution and see whether we can get some actual rule that is underlying to this phenomenon. Okay. So with that, I would like to close this presentation by giving you some broader future implications. I think this work, and in conjunction with the previous work that we saw, could be very useful in creating perceptual models, at least for healthy individuals at that time, and later by repeating the study with patients who have sensory motor control disorders, we can actually compare the responses, right, between healthy and disabled individuals. That might lead us to some interesting ways for doing diagnostics, or even later on doing rehabilitative or therapeutic measures or interventions for people with physical disability. Okay, so overall, this was an interesting piece of work for me to do, and I'm definitely interested in continuing this. And with that, I'd like to close this talk and, of course, thank Ronak and Riddhi for this work. And I'd open the floor for questions.
Thank you, Vinayak, for this very interesting talk. If audience have any question, they can use Q&A feature to ask question. And I see Jan is also online. If Jan, you have any question, you should be able to directly ask it, because I have given you the privilege of turning your mic on and also turning on your video. And if not, then let me begin with the question. So let's say if the people did extensive training, right, in this setup, how would the result might be different in that case?
That's a very good question. So extensive training would certainly, I think, for healthy individuals, I think it will lead them to get more accurate over time. Okay. Mm-hmm. But we really need to ask the question, what does extensive mean here? So for example, if you're looking at a 30-minute window where I'm doing the same task 60 times, right? Mm-hmm. For such a simple task, is it reasonably extensive or not, right? That itself, I think it's an important question to answer. Like, what's the meaning of extensive here? Yeah.
Sure. I mean, again, so what I'm getting at let's say if there's some underlying canonical task, right? Mm-hmm. And if people have done a canonical task, which is underlying, right? Which kind of transfers to this task, right? Because the task that you're doing, I'm not quite sure how much practice, people would have had outside of your setup, right?
Right.
But if the task that people were doing, and if there was some underlying canonical task on which people had practiced enough, so I wanted to hear your thoughts, how things might look in that case.
Right. Okay. Okay. So that's a very interesting point you raised. In fact, at least from our perspective, we were of the view that this is kind of based on canonical task, in the sense that if you ask a person, have you pulled a rubber band? I mean, they have some sense of what it feels to pull an elastic with both hands, right?
Sure.
So from our perspective, this was kind of a task which people would have experienced in general, on a general basis, right? Mm-hmm. But you're right. I mean, it may be possible that somebody may not really have an explicit recollection of what that experience feels. Mm-hmm. From that perspective, I think we could say this for most of the motor manipulations that we do anyway, right? I mean, if you close your eyes, you can literally pick up your phone, right? Mm-hmm. And so there are so many things that we do with second nature. Okay. So one thing we could do though is we can have a mixture of tasks. Like, so for example, and in fact, I think there are tests, I forget the complete name, but it's called Wolf's mechanical or motor test, right? Where you have a set of 17 tasks that's sort of based on these canonical experiences that people have to be able to detect different types of symmetry. So we could actually adapt this procedure for a mixture of those tasks too.
Sounds good.
Yeah, Vinayak, this is very interesting work. So my follow-up question is, based on your subject, you collect, have they done some prior training process to before do the test? I mean, do the collect the data? So I'm wondering.
Yeah.
So
Yes.
for those who have extensively trained the sensor motor kind of coordination versus just like surgeon, for instance, versus the some other person who do not have the skill sets. I wonder how much differences this might be. And in other words, this could potentially look into the training perspective, like the surgeon training or other, the military, especially because the sensor motor training aspect as well.
That's a wonderful question. Thanks, Jan. Actually, so this is sort of an adjoint work with another work that we were doing with surgeons for precise action, okay, for measuring precise action. And you're absolutely right that people who are innately trained in terms of being able to move something really, really precisely might actually feel very different because they have consciously trained on doing certain tasks and they have very very solid experience in terms of what they should feel. This happens a lot with surgeons, right? If you look at how a surgeon drills, they put in the drill and they go so fast that you get scared, but they are able to stop at the second cortex just on the basis of how they perceive the bone is going to give them how much force it's going to give them in response to their action. So I think you're absolutely right that the differences, we may see significant differences between individuals who are trained in physical tasks, like the surgical tasks, or dentists for that matter. Right? Dentists also have a very they in fact they also do something called soap carving, right? Where they have a piece of soap and they do carving. One thing though is that most of these kinds of tasks are asymmetric bimanual. So there is both hands are not really doing the same thing or according to a symmetry, like they are coordinated. So they are doing one single task. So there may also be a difference in that regard.
Yeah,
that's a very cool question. Yeah.
All right, thank you, Vinayak. We really appreciate you taking the time and presenting on behalf of the journal. So that's great. And we'll close out the session now.
Thank you very much, SK. It was a great pleasure talking to everybody. And I'll see you all sometime somewhere soon in a conference. I'm hoping to, at least.
Sounds good. Look forward to it.